Okay, I think we are live now. So is my screen clear to you, right?
Yes,
Can you
Karim.
hear me? Okay. So hello everyone, good morning, good afternoon, and good evening. Thanks a lot for being here with us and for joining this wonderful talk. Let's first introduce some small slides, and then I will give the floor to Mirna. Actually, in less than 2 days, we will have another interesting talk by Mariam Merhat, who is a researcher in Alexandria Quantum Computing Group. But this time it will be based with Washington Quantum Computing Meetup, and also some of our I mean, like new sponsors, for example, like Quantum AI, Vigno Research Center for Physics, Association Quantum, ORIONX, and also Q Mexico, and also Cambridge Quantum. The moderators will be Pavel Gura, my humble self, and also Ayodi. Uh, we also have another interesting event coming up on the 14th of October about quantum algorithms for chemistry and beyond. We will, I mean, perhaps in tomorrow or the day after tomorrow, we will announce about this event. It will be very interesting, and it will happen in the Hibata series, and also with a collaboration with Q Egypt. And also we have another interesting event that will be on November 6th. It will be about modeling a theory of gravity using machine learning. Minna al-Masri will be a co-moderator in this great event, and the event will be also with Quantum AI and also Quantum Computing Group, Cambridge Quantum, and other interesting sponsors and members. And today we have our researcher Mirna Hosny, who is a teaching assistant at the Department of Mathematics and Computer Science in Alexandria University. She is interested in non-usual ways of computation, for example, like DNA computing, and using DNA computing for quantum computing itself. She is also a researcher in Alexandria Quantum Computing Group, and I think today's meeting will be very interesting for people who come from biology backgrounds and also from a computer science background. So without further ado, I believe that Mirna Hosni can start presenting her screen right now, and I will sign off. Just a second.
Okay, thank you, Karim.
You're welcome.
Hello and welcome everyone. Welcome to our Habitio series. Today we are going to talk about non-familiar topic. It's about DNA computing and how we can implement reversible circuits on DNA computing. First of all, DNA is the biological material that is responsible for every living organism traits. It exists inside each living organism cells, and it's uh, unique for each individual and for each living organism. DNA consists of nucleotides. Each nucleotide has three parts: sugar part and the phosphate and the nitrogen part. DNA nucleotides are uh, bonds with each other with a covalent bond using sugar phosphate group, which forms a sugar phosphate backbone. This backbone is also with a sugar and phosphate, and the lifting bases are one of the four bases, which are adenine, thymine, cytosine, or guanine. A, T, C, and G. Only four letters. This is a single strand of DNA, and the sequence of these letters are unique for each person. DNA sequences can also be combined together to form what we call the DNA double helix. based on Watson-Crick principle. This principle calls C always bond with a G and A always bond with a C. C also bond with A and G also bond with a C. C cannot bond with T and A cannot bond with a G. This is the form of the DNA double helix. Okay, this is an introduction of the biology of DNA, how this DNA can work as a computer. First thing, any technology or any material that we can work as a computer, it should act two goals. The first goal is how to represent the 0 and the 1 inside this material or inside this device. Second thing, how we can swap between the 0 state and the 1 state inside or using this device or material. Using DNA, we can easily represent the 0 or the 1 with a specific DNA sequence. As DNA sequences are now known and their implementation, so it's easy to build or synthesize a specific sequence of DNA inside vitro. So we can easily synthesize a sequence of DNA that represents 0 state and another sequence of DNA that represents 1 state. This is the first step. The second step, how we can swap between the 0 and 1 states, it's easily using DNA operations inside the vitro. There are many operations inside the vitro that can apply on the DNA sequences, like denaturation, which is a double helix inside a test tube. On a on a very high temperature, the DNA double helix are broken to two DNA single strands. Renaturation is the opposite of the denaturation. Some of DNA strands are bonded together to form DNA double helix. There are also copying operations. Sequence of DNA can be copied with millions of copies in a lower time. We can also cut a DNA sequence at specific points at specific letters. We can also merge two DNA sequences. We can append a sequence on already existing DNA sequence. We can also sort a group of DNA sequences according to the length. We can also search on a specific sequence inside a group of DNA sequences, even they are single or double strand. Using this operation, we can easily change the sequence that represents the 0 state to the sequence that represents the 1 state. One of the functions the DNA computer starts with is solving hard computer problems like NP complete problem, and the first person who already done this is Leonard Adenine in 1994. He solved Hamiltonian path problem using 7 cities in polynomial time. We will explain shortly how he solved this problem with a shorter example. If we have the same problem but only on 4 cities, and the arrows represent the only possible passes between the different cities. For example, Chicago and Detroit, there is only one pass from Chicago and Detroit, but there is no pass from Detroit to Chicago. The first step, we propose a DNA sequence for each of the 4 cities. Atlanta, Boston, Chicago, Detroit. Each one of them, we propose a DNA sequence consists of 8 letters of DNA bases, and this is the complement of the proposed DNA sequence. The complement the complement is based on Watson-Crick principle. A bonds with T, so the complement of A is T. C bonds with G, so the complement of C is G, and so on. This is the first step. The second step is to present DNA sequences for the possible passes between the different cities. This is all the possible passes between the 4 cities, and this is the DNA sequence for each pass. How we construct that? For example, the pass between Atlanta and Boston, we took the second part of the DNA sequence of the Atlanta city with the first part of the Boston city. First city, we took the second part. Second city, we took the first part. And this is the pass that represents the pass between, this is the sequence that represents the pass between Atlanta and Boston. And as so on for all passes. Okay. The final step is we should find a pass using these sequences starting from Atlanta to Detroit, passing through all cities. The only possible path is Atlanta, Boston, Chicago, and then Detroit. Each city we cross over it only once, and all cities must be crossover. The resulting DNA sequences passing through the 4 cities has lengths of 24 coming from these proposals. This was Atlanta, Boston, so we took the sequence of between the Atlanta and Boston city and start with it. Then Boston, Chicago, this is the path from Boston to Chicago, and the last path is Chicago to Detroit. To merge between these sequences with a double helix DNA, we merge these paths between cities by the sequence of the cities itself. But if we use the sequence of the DNA that represents the city itself, it will not combine with the following paths because we took the same parts to form the sequences that represent the path. So we took the complement. We merge these paths by the complement of the city. Starting with Atlanta city, we took the complement sequence to bind with it, then Boston, then Chicago, and at last Detroit. This is the double strand that represents the solution of the represented problem, Hamiltonian path problem for 4 cities. Leonard Adelman the same steps, but with large amount of DNA sequences. He followed the following steps. First of all, we represent in this algorithm starting node or starting city is S, and the end node or end city is E. Step 1, generating random passes through the graph. Different passes, even they go through all cities or some of them. Step 2, remove all passes that doesn't begin with city S and doesn't end with the city E. The remaining passes will remove from them the DNA sequences that doesn't go through the all N cities. Step number 4, the remaining passes, we will remove from them any repeated nodes. If any path has any city more than once, will be removed. All these steps are done using the vitro chemical operations on DNA sequences in test tubes inside the lab. Step 5, after removing all these from previous steps, if anything remains, then it's the solution of the problem, and if nothing left, there is no solution for this problem. And this is how the NP complete problem is already solved with a polynomial time with only easily 5 steps. Leonard Adelman implementation for each city was a DNA sequence consists of 20 letter of DNA sequence, and the process is already formed as we have explained in the example, and he also combined between the process between different cities by the complement sequence of the city itself. Starting with Leonard Edelman, also after him Lepton also solved the satisfaction problem also in a polynomial time using DNA, and there is other problems has solved using DNA. The advantages of using DNA is massively parallel operations. Using a test tube has trillions or millions of DNA strands. We can only apply one operation to all of them at once. Second advantage is huge information density. So DNA, first of all, can keep the data for a very long time without any corruption or without any error happens in the data. Also, a very small part, for example, 1 gram of DNA can hold a very large amount of data, many more than any storage that we know today. The third advantage, it's clean because it's from nature itself. There is no operation on DNA can harm nature with any shape or any way. It's cheap and available all around us. Any living organism has DNA inside it, and now it's synthesized inside the lab. We doesn't for DNA computing. We doesn't use an algorithm or human DNA. No, we use a DNA sequence that synthesized inside the lab with a specific sequence used for the experiments of DNA computing. Here is some of current topic research on DNA computing. First thing is CRISPR, which is a genome editing tool. CRISPR is used as a tiny robot which is programmed to attack some cells or some virus to fix it, to fix the diseases, to fix the genetic diseases. But it's now also scientists try to use CRISPR to perform some computer operations. The second research topic is programming DNA circuits, and this is the topic we are going to talk in detail. Third thing, IBM going through to build the DNA transistor instead of electricity. Microsoft has already built a full automated DNA storage system which read and store data in DNA, and we can restore it successfully without any loss in data. And this is the shape of Microsoft DNA storage system. They encode any data to DNA sequences, they synthesize it inside the lab, and then re-decode it and correct any errors happen in the reading operation, and then they restore the data again. Another research topic is solving computer problems as NB computer problems and other even solving a maze. Maze can be built in DNA using 2D origami in DNA, and using DNA we could find all the possible paths and choose the correct one which solves the maps. Also using DNA origami they have built a tiny 7-segment digital chips that represent the digital numbers but in DNA. And one of the other topics is neural network. There is more topics, but there is some of interesting topics. And the most important one for now is for any computational device we want to use in the future, it has to contain logic circuits and logic gates to perform all computations we know for now and for more, and we need more performance in the future, especially using reversible gates, which contains no data loss or no energy dissipation. It saves the data itself. And besides the advantages of reversible gates, the advantages of DNA computer together can perform a huge computation performance. Through many researchers, there were 3 systems to implement logic circuits on DNA computer: stacking system, enzyme system, and strand displacement reaction system. Starting with the sticking system, we can implement Friedkin Gate. It was a research published in 2008. Friedkin Gate, as we know, it contains 3 bits. The first bit is the control bit, and the second and third bits are the control bits. If the control bit is 1, so the target bits values will be swapped. If the control bit is 0, the target bits values stay the same. Using sticking system, the researchers in this paper have implement for each bit a different sequence of DNA implementation. The first bit, when it's 0, it's represented with these 4 letters of DNA. If its value is 1, it's the same 4 letters but with a double strand, means bonded with their complement letters. The second bit, if it's 0, it represents by different letters of DNA, and if it's 1, the same but with a double strand. The third bit, if it's 0. Hello?
Yes, I can hear you.
Everything is okay?
Yeah,
Okay.
there is like some ticking noise. If you can, for example, change the mic, that's okay. But anyway, you can continue.
Okay. The third bit, if it's 0, it consists of DNA sequence differs from the first and second, and when it's 1, it shapes with a double strand. So if we need a full DNA sequence that represents 3 bits 0, 1, 0, so we take the 0 from the first proposal, 1 from the second bit, and the 0 for the third bit. Okay, let's test these implementations in sticking system. If we get the input we put input in the test tube with these sequences, which is 1 for the first bit and 1 for the second bit and 1 for the third bit inside the tube, and apply only one PCR amplification in the vector of DNA, the output stays the same, 1, 1, 1. But if we entered 1, 1, 0, the output should be 1, 0, 1. But after applying some of the new operations, the output was 0, 1, 1, which is not correct. If we test 0, 1, 1, the output should be the same because the control bit is 0. But the output was 1, 1, 0, which is also not correct. So if we have conclusion anything of sticking system, sticking system specifies some sequences of DNA to perform some functions, but these sequences and these functions cannot be applied on any different sequences. So these operations are different from input to input, because the input was 3 ones, if we applies only one operation, but when inputs has differed, so operations of DNA are also different, which is not reliable for building logic circuits on DNA computer, because any circuit or any gate on computer should be fixed or constant at its core, or whatever each platform it work on, but it's fixed. The difference was in the input, is in the inputs and the outputs. According to the different inputs, different outputs should get out. So sticking system is used in different topics in DNA, but it's not reliable for building logic circuits on DNA. Second system is the enzyme system. The enzyme system for also Friedkin Gate. We have 3 implementation for the 3 bits. The first bit is the control bit, is fixed as 1 always, with represented with a double strand of DNA as this sequence we show in the figure. The X input is also implemented with a double strand of DNA, and the Y also implemented with a double strand of DNA. The first test, we enter to the test tube the first input, which is 1. 1 get out as output as also 1. 1 doesn't change anything. If we enter X input to the test tube and apply some enzyme operations using enzymes besides the PCR amplification in DNA, we get the output Y, which is correct. If we input to the test tube Y and apply some different operations, we get the output X, which is also correct. Enzyme system can work as logic gates and circuit successfully, but it's very complex to use in reliable devices or in many different operations. It's very complex, and also it has one problem. The operations that applied on the inputs also different between the input and the other input. We need the operations that are applied on these inputs need to be fixed, not changed between different inputs. The third system is a strand displacement reaction system. From its name, there is a DNA strand replace another DNA strand. Two strands are replaced together. We will mention Seesaw gate. This gate is the first successful logic gate and use it to build different circuits on DNA. And it looks like it's a symbol. This pole has an input, and this is the output, and this is the fuel. Fuel is the reason to make this gate is reversible, this operation to be reversible. So when we have the fuel, we can merge it with the output to reverse the operation of the gate itself. The red numbers on the input and fuel are the concentration of the DNA sequences of DNA in the test tube, inside the test tube, the concentration of the sequence. And the numbers inside the ball is the thresholding. Each of them is a DNA sequence as we have seen in this table. And let's find example for how this operation is done. For example, this is the input at the start of the Seesaw gate. The input is a single strand and the output is a partially double strand. The fuel also partial double strand. Input means the input has a concentration, means the sequence of the input has many copies of it inside the test tube. There is not only one input, there is more than input, because one of them will replaced with the output and one of them will replaced with the fuel, as the follows. Input with the gate output is double stranded. The part that called T in blue here will combine using Watson crack with the T dash here. And starting from this point, the input strand will replace the output strand, causing the output gets the single stranded, so the output is the result now, and the input becomes a partial double stranded, means it's inefficient now. The efficient strings are single stranded for this gate, and when any strands are partial double stranded, then they are inefficient or unfunctional for now. With the same way, the input are replaced with a fuel strand starting from T bonded with a T dash here, and then the input replaces the fuel strand, so the fuel is also the output. So the input become unfunctional, but the output and the fuel are the result of the Seesaw gate. Using the output and the fuel, again we any one of them with the double-stranded input, we can reverse the operation. The T part here can bind with T dash here, and fuel will replace the input and restore the input on its original state. So this is the Seesaw gate and how it's already work, how strand can replace another strand. Using this gate, they are implemented to make it work as a OR gate and an AND gate with the same implementation, with the same DNA sequences, with the same operations, but with a small difference in the thresholding. This thresholding, what makes it work as OR or AND gate. So now we have DNA-based AND gate and DNA-based OR gate. Using these sequences, we can build any Boolean circuit inside the DNA with only AND and OR gates, because NOT gates are not available for DNA strands. The NOT gates are not available to be implemented using this system, strand displacement reaction system. So we have only AND and OR gate. And using another system which is called double rail logic mode, we can build any Boolean circuits. For example, for input square root circuit, we can implement it in DNA in double rail logic. Double rail logic is any each input will has two wires or two inputs that are represented. For example, x1 has x1 node and x11. We make this to can implement these gates and circuits inside the DNA with only AND and OR gates, because no NOT gate are available. This circuit in DNA works successfully and gets the output correctly, but it took hours to compute these square roots, and it took around 130 DNA strands through the operation. There is another system, another implementation using the same system is the DNA-based switching circuit. We build different Boolean logic circuits in DNA using switches based on Shannon switching circuits. Each switch has an implementation in DNA with a partial double-stranded, and this is in the off state. When a correct input comes to this switch and bind with this partial double-stranded, it turns to a fully double-stranded sequence, then it goes to on state. And we can, using these switches, we can implement the AND gate by two series switches, and we can implement the OR gate by two parallel switches. So for any Boolean circuits, we can implement it with two methods. First method using the double rail logic as we have mentioned, and the second method is using switch. But in implementing using double rail logic, we use DNA based OR gate with DNA based AND gate with the same system also. Strand displaced strand. Using switches, the same circuit has implemented again for input square root circuit, and it took less than 10 minutes to compute the outputs correctly, and uses almost at most 24 strands of DNA. So much better than the Seesaw gate. So using switching circuits and double rail logic, it's now impossible to build different Boolean logic gates and circuits on DNA. And it's proven experimentally is the URGL system is the most efficient system for achieving this goal. Of course, enzyme system is very complex to be used, and the staging system is not reliable for using for achieving this goal. Using these two methods, the zero-rail logic mode using DNA-based AND or DNA-based OR gates as a first method, DLG method, and using switches as a second method, it's now possible to implement NOT, CNOT, and TOFFOLI gates as example of implementing reversible gates on DNA computer. For example, NOT gate is a 1-bit gate and could be implemented in DNA using switches with only one switch, and it can only be implemented with a dual-rail logic by only swapping between the wires that represent the same input, because in dual-rail logic each input is divided into 2 wires, so we can operate the different gates and circuits with only AND and OR gates. So to apply the NOT gate, we also swapping the wires without using any other gates. For each implementation in DNA, we calculate the DNA cost and the quantum cost. DNA cost is the number of layers that contains DNA-based AND or OR gates, or layers that contains switches. The number of layers that perform the gate function is the DNA cost. So for the NOT gate, in the dual-rail logic, there is no gates inside it, so the DNA cost is 0. For switching circuit, it has one switch using one layer, so the DNA cost is 1. For quantum cost is equal to 0 for 1-bit gates, equal to 1 for 2-bit gates, and for 3-bit gates or higher, it's the count of 2 elementary gates that form this gate after decomposition. For the NOT gate, the quantum cost is 0. Let's see how we can implement the CNOT gate inside the DNA. CNOT gate has only one control bit and one target bit. Control bit can be a closed control or an open control. For a closed control, this gate can be implemented in normal Boolean logic with an XOR gate. XOR gate is implemented in dual-rail logic with 4 DNA-based OR gates and 2 DNA-based AND gates. This is a 2 layers of gates, so the DNA cost here is 2. For switching circuit, we use 4 switches to perform CNOT gate with a DNA cost also equal to. All these implementations are reversible, so if we had the outputs, we can reach the inputs again. For the open control CNOT gate, it's implemented in normal logic with a XNOR gate. XNOR gate in the dual-rail logic is the same as XOR, but it differs in the output wires. If we go slide before, the output wires here are swapped to get the XOR outputs correctly, but for the XNOR, the wires are not swapped to get the XNOR function correctly. With also DNA cost equal to. For switches, we use also 4 switches, but in different order than the previous CNOT gate, with also DNA cost equal to. Also, we have built a DNA circuit using switches. This circuit can act as a CNOT gate with both closed control and the open control, and we can function in one of them using the S switch. If the S switch is equal to 1, so the gate acts as the closed control CNOT gate. If the S switch is equal to 0, the gate works as open control CNOT gate with a DNA cost here equal 3 layers of switches. Let's see how we can implement the same way for the TOFFOLI gate. TOFFOLI gate, we implement only 2 shapes of it with 2 closed controls or 2 open controls. For the two closed controls, it's implemented in the normal logic with an AND gate between the controls and XOR gate between the output of the AND and the target bit. These gates are implemented in dual rail mode, as we have seen in this figure. The AND gate in dual rail mode is implemented with an OR and the AND gate, and the XOR are implemented with 4 OR and 2 AND gates, so totally are 3 layers. In switching circuits, we use 3 layers also of DNA switches to implement the TOFFOLI gate. For the open controls, we have the same costs but different swapping in input wires to apply the NOT, the different order of the switches to also apply the NOT gate. As we have made with the CNOT gate, we also build a switching circuit that can act as closed controls TOFFOLI gate and also an open controls TOFFOLI gates using the same S switch. If the S is equal to 1, the gate acts as closed controls T gate, and the S is 0, we can act as open controls T gate with DNA cost equal 4. The quantum cost for TOFFOLI gate is 5. So the DNA cost using switches or using DLG method, it's lower than in the cost. Using this implementation, we have implement also the half adder circuit and the full adder circuit. The half adder circuit for quantum implementation after optimization, the least cost was 4 for quantum cost. But using DNA implementations for the DLG method, the cost was 4, and using switching circuits, the DNA cost was 3. For the full adder circuit, the cost of the circuit after optimization was 8, but in DNA implementations for the full adder circuit and its reversible, for the first method the cost was 6, and for the switching circuit the cost is 4. And this table shows the all implemented gates and circuits reversibly and comparing between the quantum cost and the DNA cost, and we can show some of enhanced costs inside the DNA better than quantum. Another implementation we have built to enhance computation inside the DNA is the building universal reversible gate library. This library contains a set of reversible gates. These gates can be used together to build any reversible circuits with any size. These reversible circuits are called generators, and these generators are combined together in some permutations to perform any different circuit we need. So the proposed library is a TA library for the only one bit. It can act as only the NOT gate. As we have seen in the previous implementation, NOT gate has quantum cost equal 0, and for DNA cost or DNA implementation, just only swapping between the wires with cost equal 0.
Sorry for interruption, Mirna, but your voice is not clear.
Yes, Professor.
Can you come closer to the mic if you can, please? Thank you.
Professor Ahmed, I can't hear you. Can you repeat this, please?
I'm just asking
Hello?
Mirna to raise her voice.
As my
I think
voice?
her voice is okay.
Hello?
Okay.
Yes,
As my
Mirna, it's
voice
okay.
is
You
clear?
can continue.
Okay. This is the proposed library for the 1-bit gates and circuits. For 2-bit gates and circuits, It has 4 generators. Each generator has a CNOT gate and a NOT gate. The cost of each generator in quantum is equal to 1. The implementation of each generator in DNA has a cost equal to the implementation of this library using the first method only, not using switches. Okay, this is the 4 generators on the 2-bit library. For the 3-bit library, we add a TOFFOLI gate after the NOT gate with a quantum cost for each generator equal 6, and we have a 12 generator. For each generator there is a closed controls and there is an open controls. So we can use a sub-library of this with only the closed control generators, which are only 6 generators. So this library is actually two. One of them is the original library with 12 generators, and another sub-library with only six closed controls generators with a quantum cost for each one equal 6. The implementation in DNA for each generator is equal to 5. But in DNA we can apply a layer optimization using dual-rail logic. Inside the dual-rail logic, we can reorder the gate to minimize the layers of the DNA gates and circuits inside the dual-rail logic, but keep the same function the same. So the generators in the case 3 library can be applied or perform a layer optimization on it. So the DNA cost after optimization for each generator is equal to 3. This library extendable to any n inputs or outputs by adding extended TOFFOLI gates at the end of K3 generator with a closed control or open control, and it's only extendable in quantum implementation and DNA implementation. And this is a comparison between the library from only 1 bit to 10 bits with a quantum cost for each generator for these circuits for these libraries, and the DNA cost also. With more inputs and outputs, there is more cost, sure, but the DNA cost is always less than quantum cost. This is for each generator only. We have used this library to calculate the quantum cost for and the average for the generated circuits, output circuits. We compared our library with its 12 generators with the other previous libraries with the same size of generators and a lower size, and we get for 12 generator a minimum size, of course, because there is too many generators, but using also the sub-library with 6 generators, we get a lower length than the previous same size libraries. And the cost after DNA layer optimization is very lower than the quantum cost without any optimization, and lower than previous libraries with the same size. So we can use DNA complementation successfully to build reversible gates and circuits, and this is a very step to get a very powerful computer. So can you imagine how if we could merge more between DNA computing and quantum computing, not only implementing reversible gates or circuits from quantum to DNA, can we find a way to merge between the quantum computer and DNA computer, so we can use the benefits between the two of them to one powerful, very super computer? Because quantum computer has some difficult states to implement. For example, it needs a very lower temperature to keep the data safe. In quantum also there is no copying operation at all, but these problems, for example, can be solved in DNA successfully. So if there is a way to merge between these two new platforms to build a new computer, could be very interesting topic. This is the published paper about how to synthesize reversible circuits on the new computing. And this is the references. Thank you, and I hope you have interesting with the DNA topic. Thank you.
Thank you so much. Thank you so much for this presentation. If anyone has any question, please, I will open up the mics now. So you can unmute yourself and you can start asking. If you can't speak, perhaps you can write down your question in the chat. Any questions at all? Okay, I think there's no questions here. There are no questions. Just a second. So can you put the link for the paper back up for a moment? I couldn't write it down. Okay. Mirna, can you please write down or at least paste the link in the chat?
Okay.
And you can put the link of the DOI. Or the journal link. Okay.
There is a link. You can easily search for the title, and you can get the link directly. The DOI link is already exist here.
You're welcome. So, are there any questions? Any questions at all? Okay, I think this
just a
concludes
moment,
the meeting.
Karim.
Yeah,
I'd
yeah.
like to write
Sorry.
something on the comment.
Okay, can I stop sharing my screen?
I think that's okay. No problem.
Okay.
Okay, Karim, I added the link for the paper if anyone is interested to.
Okay. I also did the same. Okay, no problem. So, thank you so much for being here. This concludes the meeting. Please don't forget about Saturday's meeting with Cambridge Quantum Group and Warsaw Quantum AI, Q Mexico, and other great sponsors for the upcoming session with Association Quantum, and also for the meeting of October the 14th. Okay, this is going to be very interesting, especially for quantum chemistry. And that's it. Thank you so much, and good night, everyone. Okay, I will stop the recording right now.
Okay, thank you everyone.